Okay, and of course this semi-gradient method can also be is also applicable for n-step bootstrapping, right? Also with a mild change. The n-step bootstrapping, just as a reminder, is the continuing between TD0, one-step TD learning, and TD1 or a Monte Carlo approach. And of course, again, once we define it, the gradient approach for Monte Carlo and the semi-gradient approach for TD0, we can also very easily define it to all of the continuum in the middle. Again, we've seen before the n-step bootstrapping approach, and an n-step semi-gradient approach would again only require a simple modification from the tabular setting, and as before, this is in the way that we update the tunable parameters instead of updating the table entries, right? The entries for each one of the states. Now we update our approximator, our function approximator. Okay, let's look at a different optimization approach. I mean, gradient descent is one way, but there is another way to optimize. Actually, there are several ways to optimize, but there's another interesting one for, well, our purposes, for training a function approximator. So far we've seen a gradient descent approach where we update theta in each iteration and we try to find a fixed point where theta doesn't change, meaning that the gradient is zero. If we found such a point, then we can stop and say that we converged on a local optimum, right? The gradient is zero, meaning local optimum. Another approach that we commonly use in convex optimization, or even in non-convex spaces, but in order to find the local optimum, would be to solve this optimization problem in a closed form. That is to compute directly the fixed point, the point in which the gradient is zero, or the point in which updating theta, the tunable parameters, will not change them. They are at a fixed point. How can we do that? So actually there's a nice way of doing that. Specifically if we assume a linear function approximator. Or at least that's what I'm going to show you next. How to do it for a linear approximator. It might be the case that we can also do the same trick in other type of approximators, but it might be very complicated. And for the linear approximation case, it can work very nicely. It was shown to work very nicely. So as before, a linear approximator means that we have one tunable parameter per feature in our state space, per feature that all of the feature vector that represent each one of the states. We have a single weight affiliated with each of those, right? And so our approximation value is simply the dot product between our feature vector for each state and the weight vector. In this case, yeah, we can call it the weight vector. Okay, so let's play around with the math and see if we can come up with a closed form solution to requiring that theta t plus 1 will be equal exactly theta t. That is, we'll take a gradient descent step and nothing will change because the gradient is zero. Okay, so we're writing out the update rule, the TD update rule for semi-gradient methods here. Now the interesting thing is that with a linear approximator we can easily define the gradient in our approximation, which is
f of s.
Right, it's a very simple gradient. It's simply our feature vector, f of s. This is only the case, by the way, again, for linear approximators. For other types of approximator, it can be more complicated, or, well, different. But in a linear approximator, this is indeed the case. And so, let's write out the update rule, the TD update rule, in that form, while changing the gradient in our approximator with the f feature, the feature vector. And now we can simply move stuff around and try to isolate our theta vector, our weight vector. Okay, so you can see that we can take all of these values, all of the parameter, the coefficients that are multiplied by our theta, the weight vector, and the other coefficients or the other values that are not multiplied by this weight vector, and we'll just call those as B and capital A, where small b is a vector and capital A is a matrix, right? And you can easily see that small b is simply the reward multiplied by the feature vector of S of t, sorry?
The last one.
Sorry, right.
Yeah.
It's not this one, it's this one. Feature vector of S of t, and the capital A matrix is all of these values, right? This multiplied by this, right? So it's just rearranging everything. I mean, I didn't do anything fancy here. I really just rearranged the terms, and I called it small b for those that are not multiplied by our weight vector, and I called it a capital A for the matrix that is multiplied by the weight vector. That's it. Nothing fancy. But now we can define our fixed point. What is the fixed point? That is the point where theta t plus 1 will equal theta t. This is the point where b minus a theta t will be exactly 0, right? And this will cancel out, and theta t plus 1 will equal theta t. So we would like to compute this fixed point. Actually, we would like to solve it for theta t. We would like to compute this weight vector for which the update will be stable. Theta t will not change, right? The gradient will be 0. And so now we can just again rearrange this expression and see that the stable theta t is at a to the power of minus 1, the A matrix to the power of minus 1, multiplied by the B vector. Okay, just as a reminder, I hope you're on top of your matrix notation. So we don't do B vector divided by A. There's no notion of dividing by a matrix. We do a matrix to the power of minus 1. Usually it's the same with other algebraic equations, but in matrix notation it has a bit of a different meaning. But this is the correct algebraic expression. Okay, and so this is now we can define the least squared TD learning, or Lstd method, which is a closed form of expression to compute, or the closed form method for computing our weight vector for linear approximators. How does this work? We approximate the capital A matrix and B vector. We approximate these online after interacting with the environment. And each time we approximate them, we solve for the stable theta. Okay, and we can do it as we interact with the environment more, we have a better estimation or better approximation of capital A and small b, and thus we have a better solution for theta. And as before, the B vector is simply the expected reward multiplied by the feature vector of the expected state that we see, or the expected transition when we interact with the environment. And the A matrix is, well, the expression that we concluded in the previous slide, right? And again, we compute this this approximated value as a moving average of all of the over all of the states that we actually observed. Okay, again, in general, it's an expectation over the states that we encounter under our current policy, but we simply approximate that by averaging over the state that we actually observe. And this is why more interactions with the environment will get us a better approximation of this capital A matrix. But, as we saw previously in our, as we saw here, right, the expression that we're trying to solve requires an inverse of the A matrix. And there might be a problem here because not all matrices are invertible, right? Specifically, the A matrix, capital A matrix, is not guaranteed to be invertible. That is, it might have zeros on its diagonal. And this is, of course, a problem for us. So what we do, in this paper, they added a small trick where they add a small constant, epsilon, to the diagonal in order to ensure that the matrix, the capital A matrix, is indeed invertible. Okay, so in the paper you might see the A estimation of the capital A matrix following the mathematical definition plus a diagonal of epsilons, of some small values. Right, just recall that I matrix, the I matrix is the identity matrix, it's just a diagonal matrix of ones. And the B vector is approximated simply by averaging over all of the states and rewards that we observe throughout our interactions with the environment. And this is the pseudocode for the Lstd method. It has some extra tricks for doing the computations more efficient. For instance, instead of storing and updating an estimation of the capital A matrix, we directly store the inverse of A instead of A itself and then inverting it. Okay, so this is more computationally efficient. And also we do incremental updates instead of storing all of the transitions, all of the interactions with the environments, and at each step computing the average over all of those. We keep a moving average or some incremental estimation of the inverse of A. Okay, again, this is a computational trick that helps a lot with efficient computation. And so, what's good at the Lstd method? So Lstd method directly computes the TD fixed points, right, which can be very effective. It doesn't require us to converge on it. It is actually proven to be the most data efficient form of linear TD0, semi-gradient TD0, semi-gradient TD learning, but it is also more expensive computationally. It might not matter. It might be the case that you have very expensive interactions with the environment, yet very cheap computational resources. So that might be fine, but if that's not the case, then it might not be a good choice of algorithm. Semi-gradient TD learning, specifically TD0 learning, requires memory and per-step computation that is only an order of D, where D is the number of state features. In the incremental update version, the most efficient Lstd version, capital A matrix is an outer product, a column vector times a row vector, and thus requires a matrix update. The update computational complexity is an order of D squared, and the memory complexity is an order of D squared. So this can be significantly slower than the semi-gradient TD0 method, specifically if you have very high dimensional state spaces. Question, yeah?
Professor, you mentioned that for the semi-gradient TD0 approach, there's no guarantees that it will converge on a local optima. Mm-hmm. Would that guarantee exist for the least squares TD approach?
So the least squares TD approach, we compute the local optima, right? So there's no convergence. We don't perform converging steps. We directly compute the local optimum, right? So I wouldn't say that there are, I don't know if I should call it convergence guarantees. It computes the converged value, right? There's no converging steps.
You also mentioned that you approximate it as you collect samples. So does it have to be on policy or off policy or online?
So it can be. The main problem is that the fixed point is for a specific, assuming a specific distribution of the samples. So it's not a real discussion. It's not an appropriate discussion here whether it is on policy or off policy. It does require that the samples that we collect are coming from the same distribution as the fixed point. But again, this is a slightly off-point discussion for this algorithm.